Welcome back for the last talk of the morning session. The speaker is Franco Flandoli from the Scuola Normale Pisa, and he will tell us about Euler equation and Navier-Stokes equation with limit perturbation.
Thank you so much. Well, thank you for the invitation. My subject, the part of physics where I try to apply some probability and PDEs is fluid dynamics, and is not so common to have problems concerning renormalisation. I detect, turbulence is very rich, but it's not easy. I work all the summer on an idea that I wanted to describe here, but I didn't succeed, so perhaps in December. So it's very, very unsure. So I will describe a very particular problem. The renormalization is extremely simple, just to have an example that maybe could be. So I apologize for the simplicity compared to other questions, but it's another framework in which it's not easy to find examples. It will be a connection between Euler and Navier-Stokes equation with noise. The usual connection, as I will recall later, is that Navier-Stokes perhaps converges to Euler, is a famous open problem, except for some result. But here the question is the opposite, because I put random perturbation of quite specific form in both equations, and taking a special scaling limit over this multiplicative noise of Euler, I will try to detect Navier-Stokes with additive noise. The notations, as usual, U is the velocity, which is divergence free, and the rotation of U is the vorticity. And these two symbols will be the noise in the two different equations. Since the subject is probably the only talk in this workshop on this subject, let me recall just two slides to put these two particular equations into a research framework. This Navier-Stokes for the velocity and pressure with additive noise is probably the model inside the fluid mechanics, stochastic fluid mechanics, that received most attention. And maybe, since we talk a lot about physics, let me mention that even Kolmogorov suggested this model essentially because of this identity. The identity is true in dimension 2. Dimension 3 we don't know, which says that the input of energy due to the noise is very controlled. If you put a deterministic force and you do the energy balance, there is the work done by the force, the scalar product between force and velocity, and they can be orthogonal, non-orthogonal. It's not clear which is the input due to the force. In this case, in the average, the input of the force is really very clear, and so, for instance, when U is a stationary process, so you cancel the value at time 0 and at time t are the same in the average, then the dissipation is equal to the input, and it is a way to see that the assumption of Kolmogorov turbulence theory that the dissipation remains constant in the limit when nu goes to 0 could be reasonable in some model. So this model has potentially interest for turbulence and other reasons. And much work has been devoted to try to prove well-posedness, because as some people here know, a stochastic differential equation have a better well-posedness property than the corresponding deterministic one, sometime, and so people tried for a long time to try to prove that in 3 dimensions the noise may improve the theory of well-posedness, but the problem remains essentially open after many progresses. Also ergodic theory, like Martin Eyler, Jonathan Mattingly, many others did a lot of work on ergodic theory, but I don't want to mention. The number of papers on this model is really huge. A little bit less studied is the Euler without viscosity, and the noise. In Euler there is a question which noise could be interesting. A number of people believe that this noise, which has the same transport structure as the inertial term, could be the most interesting one. For instance, there is a paper of Daryl Holm producing this kind of equation and many others with this kind of noise from a sort of stochastic Lagrangian principle, and other reasons like the fact that there are physical quantities which are preserved, formally speaking at least. If we put this noise in the equation for the velocity, it is the kinetic energy that is preserved. In the vorticity formulation, in the previous at the beginning I wrote the vorticity formulation, not this one. In the vorticity formulation, if you put the same noise, it is the entropy which is preserved. We don't know, it's not possible, it seems not possible to put a noise which preserves both in 2D as it happens for the deterministic model. And so this equation attracted some attention, and there are investigations. There is some intuition, but maybe I can miss this intuition. Personally, one of the projects that I try to have is to try to prove that a suitable random perturbation improve the mathematical theory of the equations. Even in 2D, Euler equation is rich of open questions of uniqueness. And so I tried for a long time. Still, I have only there are only fragmentary results. For instance, with Massimiliano and Enrico Priola, we proved that exactly this kind of noise may prevent point vortex collision. In 2D, there are explicit examples of point vortices which collide in finite time, and this kind of noise prevents the collision of this. So it could have some regularizing effect, but a real big theorem of uniqueness of LP solutions under this noise is still unsure. But this is in a sense a motivation for what I'm going to describe.
Excuse me, could you comment a little bit on what you just said, that it prevents point vortex collision?
Yes.
Can you have a quick argument? I'm interested.
If you perturb, first let me say there are configurations of point vortices with special intensities like +2, +2, -1, which in finite time collide. If you perturb each vortex by an additive noise independent, it's very easy to conjecture that they will never meet. The point is that I want to perturb with a noise which is space dependent, but is the same noise for all points. And so this is much more difficult. It's a Lagrangian noise which could, for some reason, merge with the Lagrangian dynamic and accept collision. In particular, if the noise xi is just time-dependent noise, they collide. So the reason is that one has to take a noise which is space-dependent with a structure of the correlation which is quite strong in the sense of producing separate displacement of particles that are nearby. So if you take an infinite series, for instance, of Brownian motion with coefficient depending on space, this noise has a lot of has a property of separation of points which prevents them to when they are very close each other. In some sense, it gives this little perturbation. Another way to explain is that it's known that for almost every initial condition, collision does not occur. So in some sense, the effect of noise is to do the same as almost every initial condition, to perturb a little bit. But if you just put a noise depending on time, they collide, because it's just a Galilean transformation. But a space-dependent noise can prevent collision.
What kind of noise do you actually study here? Is it just a space-time white noise?
No. It will not be exactly space-time white noise because it is in multiplicative form, which is too difficult against the gradient. The eta there is space-time white noise. The eta on the Navier-Stokes, even worse, is the gradient, the orthogonal divergence of a space-time white noise. So it's the first derivative of space-time, but not the noise in the Euler. Not the noise in the noise in the Euler must be more regular, and I will explain in a second. So, so here, sorry, this slide is just to remind that I want to study these two equations in vorticity form instead of the form I wrote before, and this is just to say that I'm not studying the problem when the viscosity goes to 0. So it's a completely different question. Just this slide is just to say this is not my question, even if this is one of the two most important problems in two-dimensional fluid mechanics. So my point is to go the opposite way, from Euler to Navier-Stokes. So I take a noise that will be written in the next slide, parameterized by n, and I want to show that in the limit I get the Navier-Stokes with additive noise. In a sense, the nonlinear part plays a moderate role, in the sense one could think that behind there is a general principle that this kind of multiplicative noise converges to this kind of Einstein-Uhlenbeck. Unfortunately, I can prove this only in this very particular case, so I don't know how general is the principle. Yes.
How many dimensions are we?
Sorry, 2 dimension. Here is written, perhaps, yes, sorry. Yes, 2 dimension. Yes, otherwise the equation for the vorticity is not that one. There is the stretching term which changes completely the picture, yes. So this is on the torus for simplicity, 2 dimension, and here finally the formula for the noise. It is a finite sum that will converge to an infinite sum. The coefficient sigma k will be written in the next slide. Sorry, just to adapt a little bit notation slide after slide. K is in Z2, so is, beta k are Brownian motions, scalar Brownian motions, and the epsilon n will go to 0 and will compensate the fact that this series will blow up, diverge. So in some sense I will introduce a noise in which the part which is space-time blows up when n and is compensated by a small coefficient. Again, the same equation, the formula for the noise, and here I write what are the coefficients sigma k. I take the usual sine, cosine orthonormal system, and this is the important part. These are vector field. The sigma k are divergence-free vector field, because also the noise is like U, so it must be a divergence field, free field, and the divergence-free structure is given by this k perp, very important, divided by 2, divided by k2. So is this sigma k goes to 0. Like 1 over k, and it's necessary to compare with a sort of scale of noises to understand the questions. So I write the same, essentially the same noise, except that this is already infinite dimension, and with the parameter gamma instead of 2. There was written 2 in the previous one. And let me mention that gamma equal 1 would be white noise, space-time white noise, except for the fact that it is a sort of divergence-free analog of space-time white noise. Gamma equal 2 is, which is our case, but I take a finite sum. Gamma equal 2 could be thought as a divergence-free analog of a sort of Gaussian free field noise, which is very important and perhaps quite intrinsic of some kind of investigations here. And gamma greater than 2 is the only case that can be investigated by traditional method. So the only case in which this noise can be integrated in a multiplicative form in the PDE is when gamma is greater than 2. So gamma equal 2 is the threshold, is the limit case that we don't know how to put this infinite dimensional noise into the Euler equation multiplicatively. And gamma equal 1 is completely outside the present possibilities. But I want to mention this because this audience is extremely strong in renormalizing to higher and higher levels. So gamma equal 2 is in a sense the logarithmic divergence, and this is untractable for me, but I don't know. To see immediately why gamma equal 2 is a threshold, the question is to rewrite. I'm sorry that when I wrote the equation I forgot to emphasize that the noise is multiplicative in Stratonovich form. So it was gradient of the solution, I write here the same Stratonovich noise, which is from the physical viewpoint the correct operation, but it is clear that to have a mathematical theory we have to rewrite Stratonovich in Ito, and the corrector shows the importance of gamma, the gamma. Okay, please accept that the corrector is this. Maybe you remember that the corrector is the vector, the field he applied twice in some sense. The corrector is this, and as I will show in the next slide, gamma greater than 2 produces a finite corrector, gamma equal 2 produces plus infinity. And so the corrector diverges for gamma equal 2. This is the computation. I mean, it's clear that for a talk the computation maybe is not so essential, but just to say that at the beginning one manipulates using the orthogonality of k perp against the gradient of sine and cosine, then use some grouping in the wave numbers, and then some cancellation. There are the terms outside the diagonal vanish because you apply some symmetry rule. At the end of the story, after some easy computation, the corrector is the Laplacian. The corrector is a linear operator over the solution omega. The corrector as a linear operator is the Laplacian multiplied by a coefficient, and the coefficient is finite only for gamma greater than 2. For gamma equal to diverges logarithmically. And so clearly one thinks to modify the stochastic equation in order to accommodate gamma equal 2 by a renormalization, but I didn't succeed to do that. Some people told me that this is a divergence in the variance in some sense, not in the mean. And so what I will do is to compensate the divergence multiplying by a small number epsilon n in front, and not simply subtracting the mean. Let us see more. So Ito Stratonovich shows the threshold gamma equal 2. For gamma equal 2 it diverges. But what I will do is to take the finite sum for gamma equal 2 and multiply by epsilon n. I just said this. In this case, if epsilon n is 1 over square root log, then this quantity converges to a finite limit. So I will find the Laplacian with a finite constant. This seems to be, in some sense, the explanation of the final result, but absolutely is not, because the key issue is what happens to the martingale term, to the Ito term. We move the Stratonovich into Ito. The corrector produces a Laplacian, but the Ito, it depends on the Ito term. Completely depends on the Ito term. I will explain why. Let me summarize until now, because there are several notations I don't want to lose. So this is the Euler with the noise. The sigma k that I want to take are divided by k squared. The epsilon n will be 1 over logarithm. The Stratonovich was rewritten as Ito, which is martingale, and Laplacian, which due to the epsilon n, the coefficient in front of the Laplacian will converge. So this dissipative part is perfect, but the Ito part is absolutely essential. in the sense that for finite n, this is not a dissipative equation. The sum of these two is the old Stratonovich term, which preserves entropy. There is no dissipation at all. So this is not a dissipative equation because this is a fake Laplacian. It's a fake Laplacian. And so the point is, what happens in the limit? In the limit, we still have a fake Laplacian with the martingale which compensates and reproduces a Stratonovich term which conserves quantities, or we have a true Laplacian with something. This is the question at the end of the story. The martingale term is written here, so there is this small coefficient in front and the sum with these coefficients which are not easy, let's say. And here is written what I just said, that the martingale term depends on the solution in a very strong sense. If the dependence on the solution is maintained in the limit, presumably in the limit we have a martingale term which is of similar shape, taking limit of coefficients, the Laplacian, and the sum of the two is a Stratonovich term which is of hyperbolic type, and no Navier-Stokes, let's say. So this is the question. Can we break the dependence on omega in the limit of this martingale and get an additive noise, just a Gaussian additive noise? This is the point that I want to show. The martingale term is rewritten again, and I want to show that it converges to a space-time white noise with this divergence, orthogonal divergence operation in front. This is vector valued, and this is a divergence made in the skewed way. Space-time white noise in the sense, this is the Brownian motion which produces a space-time white noise taking the derivative in time. And in the limit, I will try to obtain this Navier-Stokes equation. This, since I already comment about the problem that I jumped this slide. This fact that the martingale produces a Gaussian process in the limit is a martingale which depends on the gradient of the solution. This is very strange, and in fact I can prove this only in a particular regime, namely when we investigate these equations with respect to the so-called entropy measure introduced by let me mention Sergio Albeverio and collaborators, but probably in the physical literature was introduced also by other people. So it was understood 30 years ago, more or less, that in 2 dimensions there is an invariant measure in a proper sense for Euler equation and also for stochastic Navier-Stokes, an invariant measure which is Gaussian, called entropy measure, is given by formally speaking, is given by e to the power minus beta the entropy in let's say in d omega, and the entropy is the integral of omega squared. So it's a Gaussian measure that was understood to be invariant, at least formally, at least infinitesimally, with respect to the generator. And I have to work in that regime to explain, to obtain the result. And there are preliminary facts that may help to understand. If we consider the Euler equation with the noise more regular, gamma greater than 2, I said for gamma greater than 2, the corrector Ricto Stratonovich is finite. We can study the equation. We can study the equation in that particular regime of the entropy measure. All this research is done with my collaborator Dejun Luo from the Academy of Science in Beijing. And the result for gamma greater than 2 is that there exists a solution for this Euler equation. It is weak in the probabilistic sense. There exists a probability space, etc. It is very weak in the analytic sense, but I don't want to spend time on this. because it is a solution with values in this negative Sobolev space. And so you have to figure out that one has to give a meaning to this product when omega is in this very negative space. And this solution is a stationary process in this space with continuous trajectories, and it is white noise in space at every time. So it is not a Gaussian process. In time is not Gaussian, but in space is Gaussian at every time. This white noise is nothing else than that entropy measure written there. And we tried a lot with Dejun to obtain a similar result for gamma equal 2 with some kind of renormalization of the average or so, but we don't see a way to do that. So maybe let me jump. This slide was to explain that the Euler equation with that kind of noise was studied in other regimes. For instance, when gamma is more regular, one can study that Euler equation in spaces of functions, not in the space of distribution. For instance, I have a paper with Zdzisław Brezniak and my student Maurelli, and we prove existence of solution in which the vorticity is bounded, and also uniqueness adapting the Udovich. Below, maybe this comment has something to do with the talk and specifically the motivations. Below bounded vorticity, one should keep in mind that to the Euler is not well posed. Uniqueness is not known. Only for bounded vorticity, uniqueness is known. Below, not. Even if the vorticity is LP, I'm discussing vorticities which are distributions of class H minus 1 minus. So uniqueness is absolutely out of question for the deterministic 2D in that regime which is below L infinity. But now comes what I said at the beginning of the talk, that I try to use noise to restore uniqueness. And so this is why I try to use noise, and noise as rough as possible. So I try to go in the direction of gamma equal 2 to restore uniqueness. The approximating system, the one in which this special noise is just finite sum, has exactly the same theorem. We can study, we have stationary solutions, white noise at every time. This is not Galerkin, this is not a finite dimensional system. The noise is finite dimensional, but it's Euler. It's Euler with finite dimensional noise. The solution is white noise at every time, same regularity. Let me only add a name. For the sequel of the talk, I will call the white noise solutions these stationary processes which are white noise at every time. So I have a sentence to explain immediately this idea. Solutions which are white noise at every time and stationary. And finally, the main result. Now, if we take white noise solutions of the system with finite noise, and this epsilon n scales, as I said, the solutions converge weakly to the solution of Navier-Stokes, which is unique. So we cannot prove uniqueness for the Euler with that kind of noise, unfortunately. The point is that in this special scaling limit, we get an equation which has a unique solution. So the intuition that there is some uniqueness behind is correct, but is not a theorem for Euler. It is a theorem, known by other people, for the limit equation. This limit equation was studied by Giuseppe da Prato here, and Arnaud Debuche, Albeverio, Ferrario, and many other people also here. And they proved uniqueness even in the strong sense for solution with values in negative Bezos spaces, etc. The equation I wrote in the previous slide, is the vorticity form. Usually, da Prato de Bush, for instance, consider the equation for velocity with additive space-time white noise. which is a vector field, because the equation is for a vector field U. So the noise is a space-time divergence-free field. And I take this gradient orthogonal, divergence orthogonal of this noise. And this is my equation, which has uniqueness, even pathwise uniqueness. The scheme of the proof is already clear from the discussion, namely we rewrite Stratonovich as Ito plus correction. The correction we understood already that converges to a Laplacian, to the correct Laplacian of Navier-Stokes. So the problem is only to explain why the martingale term, which includes the solution, converges to a Gaussian process. And it's a question of covariance. So I take again the martingale, rewritten many times again, and I take the joint variation. No, I said covariance, wanted to say quadratic variation. So it's a question of quadratic variation, not covariance. So I take the joint quadratic variation between the martingale against against the elements of the Fourier basis, and we have to prove that this quadratic variation converges to the analogous quadratic variation of the Gaussian process. For the Gaussian process it's very easy, because W is a space-time white noise, so simple drop the detail. At the end of the computation, this joint variation is delta in the Lm, in the indexes of the basis, and L square in with respect to the wave number. The wave number appears as square. So we have to prove that the quadratic variation of this martingale depends on omega, converges essentially to L square. And the point, it is here that there is a simple, let's say, renormalization that I try to explain. This martingale is the damping factor, fundamental, times, it's not very visible, this is M tilde, because I want a name for the martingale without the damping factor. So M tilde is the same martingale without the damping factor. If we do the same computation for M tilde, in some sense the basic computation is for M tilde, and then you put the damping factor, which works. The same computation on this for M tilde. Okay, the formula is long to digest, but omega is our white noise solution of Euler, which is Gaussian in space, is white noise in space. If we take the expected value, we can use the fact that omega is white noise in space and simplify very much. It is done in the next slide. Here I rewrote the formula for the joint variation of M tilde, and take expectation, jump the detail. The result is precisely L square multiplied by this logarithmically divergent term. So if instead of M tilde we use the damped M with the 1 over square root log in front, this term is compensated, and we find precisely the joint variation of a Gaussian process. This computation is the typical understanding of renormalization of logarithmic divergences, which for me is, for myself, is less common because I don't read usually the quantum literature, but it was already known in fluid dynamics. So I want to mention that inside the fluid dynamic, it was understood that the kinetic energy associated this entropy measure is in a space such that the velocity field U is a distribution of class minus epsilon. So the kinetic energy is infinite, as one can read immediately by Fourier, is infinite. But subtracting to the random field given by the kinetic energy, the average, people 20, 30 years ago proved that this renormalized kinetic energy converges in L2 and also other LP with respect to this entropy measure, and called this the renormalized kinetic energy, which in fact is a renormalized. It corresponds to interaction energy. If you replace the random field with point vortices, this is the interaction energy of the point vortices. So this energy, the interaction energy is finite. The full energy is not finite and is necessary to subtract. And more or less this expression, if one compares with the previous slide, are the same. What we have to do is to take, if we take the M tilde that has a divergent expectation, and we subtract, we can prove that the difference converges in L2, very similarly to the kinetic energy. But then what happens when we put the damping coefficient epsilon n in front? It happens that the part in the expectation converges to a finite limit, and this difference goes to zero. And so at the end of the story, so the renormalized part, with the coefficient 1 over log in front, now there is no more tilde, goes to 0 in L2 mu. And the expected part with the logarithm in front converges precisely to L square, which was the covariance of the noise. This is the explanation why in the limit this strange martingale depending on omega, suitably rescaled, only the part which is Gaussian survives, the other part goes to 0. And sorry, perhaps I was a little bit fast. This is the last slide in which I try to explain other reasons, maybe some of them already mentioned, about why I studied this problem. The fact that a Laplacian erases is clear from Stratonovich to Ito, but the point is that it should not be a fake Laplacian. I remember a discussion with Heinrich and Maxime Auré, others in the past, for a model which is not exactly this one. We had in mind particle systems perturbed exactly by this kind of noise. So, in a sense, a particle system in which this clarifies also the question about point vortices. If you have particles in which there is the interaction part of the particles, and then we put this noise, let's say in dt, which depends on space, and in space we put the position of the particle. So the particles interact in some way, and each particle feels the same noise, which is space dependent. And the intuition that we had a time ago was that if we take a noise, with the correlation very short, at the end of the story, that noise behaves like independent Brownian motions when acts on different positions. Of course, when the positions are really very close, there is a question. And in some sense, and sorry, I forgot to say that if instead of this noise we have additive independent noises, then the mean field limit of this is a parabolic, non-linear parabolic equation. There is a Laplacian. So the fact that the true Laplacian with parabolic features appear in the limit with such kind of noise, in some sense was conjecture. Perhaps with the particles can be proved in other regimes. At the PDE level, I was able to prove it only in this special regime of stationary solutions with respect to the entropy measure. In some sense, the fact that the solution is a stationary white noise in space is perhaps the origin of the fact that the limit martingale is a Gaussian process. So I don't know how much one can extend this argument. At the moment, I don't have idea how to extend this argument. Presumably, I can extend it to non-stationary, but with initial condition absolutely continuous with respect to that measure. But I don't know how much one can go further. And as I already remarked, we spend a lot of time with Dejun trying to prove uniqueness due to noise. Especially we had different intuitions that gamma equal 2 could be relevant, and you see for gamma equal 2 we obtain this Navier-Stokes equation which has uniqueness. So obviously what we are trying to do now is try to use this uniqueness backward, but we don't know how to move to the true Euler in some sense. And so more or less these are the ideas. Thank you very much.
So about these particles, can you look at the, say, Hamiltonian system of particles? Then X would be a phase space point, and O would be a Hamiltonian vector field, I suppose. And is it then possible to take noise that, for example, only depends on the configuration space coordinates? Or?
The example of point vortices is precisely, I don't know any general answer to the question, but the example of point vortices is precisely Hamiltonian, and the noise vector valued with the divergence-free structure preserves a lot of properties of the point vortices. The interaction, certain invariance remains invariance, but it has the property that avoids collision, for instance. So it's possible that also for other Hamiltonian systems, this kind of noise may prevent some blow up, some pathologies. I never thought about other applications of the question, but so the interaction between this noise and Hamiltonian is very interesting, I agree.
Maybe another one. So your renormalization was basically just weak ordering, right?
Yes, exactly. Yeah. Exactly. It was just the simplest one, as I said at the beginning. is not very common in Navier-Stokes, so to find examples of renormalization. Perhaps I absolutely don't know if one can try to go to gamma equal 1 by more sophisticated renormalization. Yeah.
But I have a question. So how important was actually the Navier-Stokes nonlinearity and everything what you did? Because I imagine you could just take a Gaussian equation with
yes,
and then you get the same invariant measures,
exactly.
And then everything is still true, no?
If you drop completely the nonlinear part, the result is exactly the same. It's just a little bit less appealing because, but okay, exactly the same. For us, it came out from our research on Navier-Stokes. This is why I like to present on Navier-Stokes, but exactly.
Right, so
but it's essential to have the stationary solution which are of that form. So if you either Gaussian or Navier-Stokes or maybe KdV with noise. There are some other examples with a stationary solution with Gaussian marginal, but not so many. Okay, thank you.
So if there are no further questions, let's thank Franco and all the
Thank you
speakers
very
of the
much.
morning event.